Welcome! In this video, I'll show you how to solve problem 6.20 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, I believe this is the same problem as problem 6.22 from the second edition of the same book. Alright, so this problem tells us the following. It says, consider the 8 n equal 2 states. Find the energy of each state under strong field Zeeman splitting. Express your answers as the sum of three terms: the Bohr energy, the fine structure, and the Zeeman contribution. And then they ask us, if you ignore fine structure altogether, how many distinct levels are there? And what are their energies? Degeneracies. So let's go for the first part. So we want to find the energy of each state. So basically we want to apply the formulas that we already found, these ones right here, to find the energies. And they tell us that it has to be the sum of three terms, so Bohr energy, fine structure, and Zeeman. So basically everything that we have seen. Bohr energy is this part right here. Okay, so this is simply the energy that we saw in Quantum Mechanics 1, right, in the first set of lectures, and there's nothing too crazy about that. This is the Zeeman contribution, and all of this is the fine structure. All right, so if we want to find the total energy, we're going to have to add these two up. Now we're going to do it immediately, just to make sure that we can simplify this a little bit. You know, we have 13.6 electron volts here and here, n cubed and n squared, so we can factor it out just a little. But since we are going to have to do this many times, because there are 8 states, simplifying this beforehand can be really, really useful for us. You know, just save us some time. All right, so let's factor out 13.6 electron volts and n squared. So when we do that, we get 13.6 eV over n squared, and then factor of. Let's begin with this. So we get -1, and this doesn't have it, so we won't include it in here. Then we get this. So we get plus alpha squared over n, product of 3 over 4n, minus L plus 1, these of course being the different quantum numbers, divided by L plus 1/2, L plus 1. All right. And of course, we can't forget about the Zeeman contribution. So Bohr magneton external field times ML plus 2 whoop, my tablet lagged. MS. All right. So this is the formula that we will have to plug into all of our values. Of course, we are dealing with n equal 2, so we can immediately just, instead of n, plug in 2. So we get 4 here. And instead of 4 times n, we get 4 times 2, which is 8. All right. And 13.6 divided by 4 is 3.4, I believe. 3.4. You could also just leave it as 13.6 divided by 4, but it's extra things you will have to write, so why bother? Okay, so let's now go to the next page and identify our 8 states. So let's see, how will we label them? Let's use, of course, ket notation. That's going to be very useful. So we will label our states as, you know, some number. And then we will define it as its value of n, its value of L. What other numbers are relevant? Just take a look at the formula. We only need the quantum numbers that are in the formula. So we still need ML and MS. So let's put the ML right next to the L and MS at the end. You can, of course, rearrange this in whatever way you want. It doesn't make any real difference. But the importance is that you understand the significance and you keep the consistency, okay? You cannot later on just change and start writing the L here or here, because then it's going to lose its meaning and it's going to be really, really bad. All right, so n is of course going to be 2. Actually, maybe let's leave it like this here and we will change it later. Okay, so n of course is 2. That's fixed. You could of course take other levels, but we are dealing with n equals 2 here. Because of that, L is limited to being either 1 or 0, right? I hope you remember those rules that we derived when we saw the hydrogen atom. Because of this, ml is also limited, and it can only be 1, 0, or -1. And ms, this can be either 1/2 or -1/2. So maybe let's say plus minus. Okay, so these are all our quantum numbers. So let's begin labeling states. Now, again, it doesn't matter which one you call 1, 2, 3, 4, whatever. You can call them star, fish, whatever makes you happy. But usually just pick some names that will give you an idea of what it is that you are doing. So n, as I mentioned, is 2. L can either be 1 or 0. Let's begin by 0, and we will then work our way up. Then ml, if L is 0, ml has to be 0, right? ml goes from plus L to minus L. So these values for ml are actually for L equal to 1, right? So if L is 0, then of course ml is also 0. Okay. Then we need the value for ms, and let's begin with a value of 1/2. So under these conditions, what would the state be? What would be its energy? Or actually, maybe let's just write all of our states down first. Yeah, let's do that. So let's go for state number 2, and we will find the energies later. All right, so this would be 2, 0, 0, and -1/2. All right, next state, state 3. This would be 2. Now let's go up. So let's go to L equal 1. We already run out of states with L equal 0. We get 1. Then ml, let's begin at 1. And then we get 1/2. And we will, of course, have another one of these states, but with different value for ms. So we also have 2, 1, 1, and then -1/2. Then we go for the 5th state. Again, the number in which I'm writing them down is just because this is more natural to me. It doesn't really matter. The important thing is that you have 8 distinct states. Careful here. We now go to ml equals 0. Sorry, here, 0. So ms is 1/2. Now we continue. And 2, 1, 0. And then -1/2. Now I'm running out of space, so I'll continue to the right. Maybe let's change colors just to make sure that it's clear. And then we have state number 7, which is now going to be 2, 1, -1, ml -1, and 1/2. And finally, let's go for state number 8, which will be 2, 1, -1, and -1/2. Now, all we need to do is take each one of these states with their corresponding quantum numbers and plug them into this formula right here. So, and that's going to be the entire problem, basically. The issue is that this is, well, we have to do it 8 times, right? It's going to be a bit annoying, but the idea is not particularly hard, right? It's not difficult, it's just annoying. Wait, how did I even open this? Wait. Right, there we go, sorry. So let's begin with the first 2 states. So let's take these 2, copy, and paste them here. All right, so what would be the energy of the first state? So energy 1. So let's take this and just plug it in. So we're going to be using this. Oh, wait, I just noticed that I didn't write 2 in here. I just kept it as n. So I'm going to just add that. All right. So I'm lazy. I'm just going to copy this. So copy and paste it. And let's see. Now we have this L, L plus 1, and blah, blah, blah. But remember, if there is an L equals 0, then this whole thing has to be equal to 1, right? That's what we discussed before, because otherwise this here would be undefined, and that's not good, right? Undetermined, sorry. And the way that you see this, we've discussed it before, but basically the procedure we use to find this formula assumed L different from 0. So if you want to do it with L equals 0, you just go back to the initial Zeeman formula, plug in L equals 0, and you're going to find an equivalent result. So yeah, but in general, you can just use this one and keep in mind that if L equals 0, this is 1. Okay, so we get 3/8 minus 1. And then, of course, everything else. So plus for magneton, external field, and then ml, which is 0, plus 2 times ms, which is 1/2. So we get 1. So, nothing changes. So now we need 3/8 minus 1, which is minus 5/8. So this here is minus 5/8, minus 5/8. And of course, we can just multiply here, and we get minus 5/16 alpha squared. And we can also just factor out the minus sign. So put it outside and turn this minus into a plus. And there we go. So this is the first energy state, or the energy of this first state, rather. Okay, not super clean, but it's okay. All right, let's go for the energy of the second state. So we have to do exactly the same, but with different quantum numbers. So this would be 3.4 electron volts minus 1 plus alpha squared over 2, 3. And now we have 3/8. We have the same thing. This is exactly the same thing, actually, right? Because the only thing that changed is the value of ms, which went from positive to negative. So actually, we get the same thing here. So we still get minus 3/4 electron volts, 1 plus 5 alpha squared over 16. But now this is negative. So that's the only difference. All right? So those are the first two states. We now have to do this 4 more times. Yay. Okay, so let's go to a new page, copy this, go for the next couple of states, so 3 and 4. Of course, again, you can do this with whatever states you want. You don't have to do it in this order. Doesn't matter. All right, so energy 3. E3, let's go. So this would be, let's see. So 3.4 electron volts minus 1 plus alpha squared over 2. As always, just try to pause, do this yourself, and then check the result. So minus, now L is equal to 1. So we get 2 here, so minus 2 minus. ML is 1, MS is 1/2. So we get minus 1/2 over, and this is 1 times 3/2 times 2. So we get 3. And then over here, we have ML, which is 1, and this is also 1, because 2 times 1/2 is 1. So we get 2 times Bohr magneton external field. Okay, so the only thing we have to do still is figure out what this is. So 3/8 minus 2 minus 1/2 is 3/2. Divided by 3, this is 3/6, which is 1/2. So we get 3/8 minus 1/2. All right. So this, now we just take common denominator. So it's 3 minus 4/8, which is simply minus 1/8. So let's plug it in. And well, we now have to multiply by 1/2. So we get minus alpha squared over 16. And of course, we can factor out all of our negatives. So maybe let's rewrite it so that it's a little bit, more proper. So minus 3.4 electron volts, 1 plus alpha squared over 16 plus 2 Bohr magneton external field. All right. Great, so let's now go for the fourth energy level, all right? So E4, let's see. Now, don't be confused because before we had almost the same results. Oh, wait, what happened to the -1/2? There we go. But this time it's not going to be the case because before this was always 1 because of the fact that L was 0, but now L is not 0, so that's not the case. So we get, well, the minus, not yet. So 3.4 minus 1 plus alpha squared over 2, 3 over 8. All right, and then we get -2. Then we have -1 times -1/2. So we get actually +1/2 divided by 3. So this part didn't change. And this part right here, what is it? So we get 1 here and then plus 2 times -1/2. So this is -1. So we get 1 minus 1. So the Zeeman part is going to be 0 for this. Okay. Then we need to just add this up. So 3 over 8 minus, so this is 5 over 2. So this is actually 5 over 6. So let's take common denominator. We get 18 minus 40 divided by 48, right? 8 times 6, yes. Okay. So this is minus 22 over 48. We can divide, just simplify by 2. So we get minus 11 over 24. Okay, so let's plug it in. And well, of course, multiplying by 1/2, we get minus 11 alpha squared. So minus 11 alpha squared over 48. Okay, so this is the fourth energy level. Let's now go for the next two states. So 5 and 6. Okay, fifth energy level. So E5. This time we have 3.4 electron volts times -1 plus alpha squared over 2, factor of 3 over 8 minus, let's see. Now, L is 1, but ML is 0. So we get -2 divided, right? This part is 0, divided by 3. And then in the Zeeman part, we get Bohr magneton, external field, and then 2 times ms, which is just 1. So just like this. Once again, we need to figure out what this is. So this is 3 over 8 minus 2 over 3. We take common denominator. That's 9 minus 16 divided by 24, which is -7 over 24. Let's plug it in, multiply by alpha squared over 1/2. And we get the following, which is -7 alpha squared over 48. Plus, of course, the Zeeman part. Okay, sixth energy level, we do exactly the same thing once again, but changing the quantum numbers for these ones. So this time, 3.4. Well, actually, maybe let's factor out the minus signs here. I think that's what we have been doing throughout. I mean, doesn't really matter too much, but looks a little bit better. And it's easier to compare. Now, 3.4 electron volts times -1 plus alpha squared over 2, factor of 3 over 8, minus. All right, so this time we get actually the same thing, because the only thing that would change inside is this ms, but it is being multiplied by 0. So actually we get the same thing here. So we get exactly the same part that we had up there. So let's factor out a minus sign. We get 1 plus 7 alpha squared over 48 minus, right? Because this time the ms here has a minus. So minus Bohr magneton external field. Now there's only two states left. So let's go get them. States 7 and 8. Okay, so E7. Here we get 3.4 electron volts, minus 1 plus alpha squared over 2. This is the same as always, 3 over 8. And now comes something that might be a bit different. So we get minus L, once again, is 1, so we get 2. But this time ML is minus 1, so we get plus 1 times 1/2. So we get plus 1/2. This is divided by 3/2. And then we get plus the Zeeman contribution. Since ML is minus 1, we get minus 1 plus 1, so we get 0. So no Zeeman contribution. So now we only have to find this. I think we already did it, but I don't remember what it was, so I'm going to have to do it again. So 3 over 8 minus 5 over 6. Oh, this is 3/2 times 2, sorry. Okay, so here we get 18 minus 40 divided by 48. Ah, yeah, this was a minus 11 over 24, which we then plug in. So minus 11 alpha squared over 48. And we can factor out the minus sign. All right, so final state, we're almost done. E8. This is plus for now. We will factor out the minus sign later. Electron volts minus 1 plus alpha squared over 2. Get 3 over 8 minus, okay. What do we have here? So once again, at 2, this time we have minus, and ML is minus 1, but MS is also minus 1/2. So we get 3 negative signs, so we end up with a minus sign anyway. So we get minus 1/2. And then we have 3 down here. And the Zeeman contribution is going to be, let's see, ML is minus 1, then we have minus 1 again. So we get minus 2. Okay, so finally we just need to calculate this part once again, which is 3 over 8 minus, that's 3 over 6, which is 1/2. So we get 3 over 8 minus 1/2, which is going to be 3 minus 4 over 8, which is minus 1 over 8. So let's plug it in, minus 1 over 8. So we get minus alpha squared over 16. And of course, with this part right here. Okay, so those are our 8 states. So maybe let's take all of them and just keep them in one page so that we can take a nice look at them. Hopefully I can somehow make them fit. These are the 5 and 6. I don't think they're gonna fit, but we'll do what we can. E5, E4, E3. Actually, they might just fit. Damn it. Okay. Depends how large I wrote these ones. If not, I can always just rewrite them and make them smaller. Yeah, I'm gonna keep them here and just rewrite them quickly so that they can fit. Okay, so E1. This is minus 3,4 EV 1 plus 5 alpha squared over 16 plus the Bohr contribution. And then the other state is the same, but with a minus sign. So minus 3.4 EV 1 plus 5 alpha squared over 16 minus Bohr magneton external field. Okay, so let's get rid of this. Amazing. So these are our energy levels, which is exactly what was required, right? So yeah, find the energy of each state. And they are expressed as a sum of 3 terms. All right, so let's take a look at them. So each one of these, as you can see, has all of the terms that we want. So the first term is going to be the Bohr part. Then we have the fine structure, which is this part. And then we have the Zeeman contribution. Okay, so those are the 3 contributions that we have. And that is the first part that we're asked. And then they say, if you ignore fine structure, how many distinct levels are there and what are their degeneracies? So what exactly about this is fine structure? So let me copy all of this, go to a new page. So the fine structure part is basically this part right here. So what if we ignore all of this? How many distinct levels would we have? All right, so maybe let's do it like this. All right, so how many distinct levels would we have? Well, we can see everything has this minus 3.4 EV, right? Here and here I didn't factor out the minus sign, but it is multiplied by -1, so it's the same. And the difference comes from the Zeeman contribution. So we have 2 places, of course, where it is 0. So maybe let's make a small table to the right side where we can just make a brief summary of what's going on. All right, so let's see. What is the Zeeman part? So maybe let's see Zeeman part. And this is, of course, going to be basically in units of Bohr magneton times the field. And let's see its degeneracy. Basically, how many different states have that same energy? That's what I mean. So we have this state right here, which has a 1, right? It's 1 times Bohr magneton times the field. And we have the same thing here. So basically, we have states which have the energy of the Bohr part plus 1 time a Bohr magneton times the external field. We have 2 of those. Then we have, let's see, actually we have a 2 as well. So maybe just to be a bit clearer or more organized, I'm gonna do it like this. So how many have a 2? So we can see that there is 1 state here that has a 2. So that has even a higher energy. Then we have, how many have a 0? We have this and this. So we have 2 of those. How many have a -1? We have 1 here and 1 here. So we also have 2 of those. And how many states have a -2? It's only this one. Oop, I almost wrote -1. Okay, so these are the degeneracies of the different new energy levels, right? There are several that share the energies, but we can see that degeneracy is usually further broken by the Zeeman effect. That's why we call it Zeeman splitting. And this is the case for high or a strong field Zeeman splitting. So this is problem 6.20 from the Griffiths. If there's any question, please make sure to leave it in the comment section. I'll check it out. And yeah, I'll see you in the next video. Thank you very much for watching.